Hello everyone. So today we are going to start with the new module, that is Zen transforms, or we can say it as Z transform. So this is basically the third module of your syllabus. The second module we are going to do it later. So now we will start with the module. So first we'll get to the definition of Z transform. So what does the definition say? Let un is equal to f of n be a real value function defined for n is equal to 0, 1, 2 up to infinity, and un is equal to 0 for every n term which is less than 0. Then the z transform is given as z transform of un, means z transform of this term un is equal to summation from n tends to 0 to infinity un z transform of minus n, which is equal to u of z. So this is basically the definition for a z transform. So what does this definition mean? See, there is a term given as un. This un corresponds to a constant term which will be having some of the real value functions which is defined for n is equal to 1 to infinity. So there are basically numbers, and un is equal to 0 for n which is less than 0. If n is less than 0, then we can say that n are the negative integers. So this term un becomes 0 only for the negative integers. So this is the definition of a basic z transform. Z transform of un is equal to summation n tends to 0 to infinity un z of minus n is equal to u of z. This term you need to remember because we are going to do some proofs in the later time. So this term is required for that proof. So there is another way of representing this in terms of inverse z transform that we are going to discuss in the upcoming sessions. So what does this inverse z transform say? Whenever the infinite series converges, of the inverse of z transform is denoted by z transform inverse of u of z is equal to un. This you make a note of it, then we are going to explain, I'm going to explain this in the future sessions. Okay, this was basically about the definition. So now we'll get to some of the properties of z transforms. So the first property is called as linear property. So now what does this linear property say? If u of n and v of n are any two real value functions and a and b are constants, then z transform of a into u of n plus b into v of n is given by a into z transform of u of n plus b into z transform of v of n. So this property says that here the a and b are there, right? They are constants. So if you want to do the z transform of this constant term along with the functions, so since the a and b are constant, right? So the first thing we can do is we can split these two z transform. That is, we can write it as z transform of a into u of n plus z transform of b into v of n. After this, again this a and b are constants, right? So we can take them out and we can do the z transforms of these functions. Z transform of v of n. Since a and b are constants, right, we can take those outside and we can separately do the z transforms for these functions. So this property is called as linear property. So now the second kind of property is damping property. This property is a very important property and would be used in many problems in the future sessions. So what does this property say? Let z transform of u of n is equal to u of z. Then we have two conditions for this damping property. They are z transform of a power n into un, this un corresponds to a real value function, is equal to z transform of u of n, in which z is replaced by z by a, which is equal to u of z by a. We know the basic z transform definition, right? That is, z transform of un is equal to summation n tends to 0 to infinity un z minus n, which is equal to u of z. But in this case we have written that z is replaced by z by a, so automatically this becomes u of, it was u of z, right? So it becomes u of z by a. And the second condition is z transform of a power minus n into u of n, which is equal to z transform of u of n, where z is, now here it is replaced by a into z, so it becomes equal to u of a into z. So now we are going to prove these two conditions of the damping property. So now let's prove them. So now we'll prove this, the first case, that is z transform of a power n into un is equal to u of z by a. Now by definition we know the basic definition of a z transform, that is z transform of un is equal to summation n tends to 0 to infinity un z to the power minus n. Now let's consider the left hand side, that is z transform of a power n into un. And now in the definition we will substitute the condition. Here in place of un there is a power n into un, so here also we will substitute the same thing. So here we can simplify some terms, that is, let's take un to one side and let's write these two terms together. So now by substituting here we can see that z to the power minus n, right? And this is a power n. So now let's bring this a power n to the denominator. So by bringing a power n to the denominator, what this becomes? This becomes a to the power minus n, right? So now here let's take this minus n common. So how we can take this common? We can write it as z by a to the power minus n. So here we can, if we see this carefully, this becomes the z transform of z by a. So we can write it as z transform of z by a. So we can write it as z transform of z by a, because in place of here z there is z by a. So this also can be written as u of z by a. So here we have proved the right hand side part, that is z transform of a power n un is equal to u of z by a. So now similarly we will prove the second condition. So this is the second condition, that is z transform of a power minus n into u of n is equal to u of a into z. So now we need to prove this RHS by considering the LHS, that is z transform of a power minus n into un. So now by using the definition in this case as we have used in previous problem, so replace this un by a power minus n un into z power minus n. So here we can see that a power minus n and z power minus n, both the powers are minus n, so we can multiply the bases together and take the power outside. Az to the power of minus n. So again this corresponds to z transform of Az. Also it can be written as u of Az. So now again we proved these two conditions. One is z transform of a power n un and z transform of a power minus n into un. So now we will get to some standard z transforms. So now we are going to discuss some of the standard Z transforms. So there are few standard Z transforms. That is, the first Z transform is for Z transform of a power n. So these standard Z transforms you are going to apply in some of the problems. So now we'll prove this. So what would we get the final result for this? So for that we need to consider the definition. Again, we know the definition, standard definition says that Z transform of u of n is equal to summation n tends to 0 to infinity un z power minus n. So now here we know that in place of un we have Z transform of a power n. So in place of un, so we need to substitute as a power n. So again now we need to bring this a power n to the denominator. So what will it become? When we bring this a power n to the denominator, it becomes a power minus n. Again these powers are same, we can take that outside and we can write it as z by a to the power minus n. So yeah, we need to take a by z outside, not z by a. So we need to take this z to the power minus n to the denominator. So z to the power a power minus n to the denominator. So it becomes a by z to the power plus n. Okay. If we take this to the denominator, this becomes plus n, right? So the finally we get it as a by z to the power n. So now we need to let's try to remove this summation. So in order to remove this summation, we need to start putting the values of n from 0 to infinity. So let's write the series how it becomes. So the summation, right? So we need to add the power of 1 plus a by z to the power of 2 and so on. So here there is a concept called as geometric series. The geometric series corresponds to the 1 plus r square plus r cube and so on. This is a standard geometric series. It matches to the whatever we got the answer here, because we know that anything to the power 0 is 1. So this becomes 1 plus r. So let's consider r is equal to a by z. So r to the power 1 is r plus r square plus r cube. It goes on. So this corresponds to a geometric series. So in order to make this equal to the geometric series, let's consider r is equal to a by z. So now when we compute this r is equal to a by z in this equation, so what would the equation become? Again this equation becomes like this. See, 1 plus, so let's compute this. Let's write a by z is equal to r or 0 plus r to the power 1 plus r to the power 2, and it goes on. And we know that r to the power 0 is 1, r to the power 1 is r plus r square plus r cube. It goes on. It corresponds to a geometric series. So now let's put this a by z is equal to r. So now what happens to the z transform? A of n is equal to the summation up to infinity, right? So in standard way we can write it as 1 divided by 1 minus r. So since there is no stop, right, it's continuously going on, right, so we can put it in a formula and we can write it as 1 divided by 1 minus r. So now we have substituted r as a by z. So what does it become? 1 divided by 1 minus a by z. So now we need to simplify this. That is, z transform of a of n is equal to, let's take the LCM, z minus a by z. So now when we bring this z to the, if you cross multiply it, it becomes z by z minus a. So this is the required z transform of a power n. z divided by z minus a. Also, if we substitute the values of n as 1, 2, 3, we can directly write some of the other standard z transforms. Like, so now let's put n is equal to 1. So now let's put a is equal to 1, not n is equal to 1, z minus a, it's a, right? Now let's put a is equal to 1. We know that 1 to the power n is 1. 1 to the power anything is always 1, right? Now what happens to the z transform? Let's see. Z transform of, now a is replaced by 1, so 1 power n is equal to z divided by z minus, in place of a there is 1. So therefore we can compute the z transform of 1 as z by z minus 1. So this is another standard z transform, that is z transform of 1 is equal to z by z minus 1. We are going to use this standard z transform in many of the problems. So now we have discussed two standard z transform, that is z transform of a power n and z transform of 1. So now let's discuss some more z transforms. So another type of z transform is z transform of e power a n, when the question is of the form e power a n. So how do we find this z transform? So the first thing we need to do is we need to split this, that is z transform of e power a n is equal to, we can write it as z transform of e power a to the power n. We can write it this way, right? So now if we put this e power a is equal to a, if we put this e power a as equal to a, what do we get? We get it as z transform of a power n. We have already discussed the z transform of a power n just now. What is z transform of a power n? That is z by z minus a, right? So nothing much to do. In place of a, we need to substitute as e power a. So now what does the z transform look like? E power a to the power n is equal to z by z minus, in place of a now it is e power a. So this is the required z transform of e power a n, that is z by z minus e power a. So now we'll discuss some more. So now this is another kind of z transform, that is we need to find the z transform of n power p, where here p stands for a positive integer. So we know that the positive numbers tend from plus 1 to infinity. So we can substitute the values for n p as 1, 2, 3, 4 up to infinity, and we can find their corresponding z transform. So now let's try to find the let's prove this fact that this is the required z transform of n power p. Generally we have written it 3 minus z into differentiation of d by dz. D by dz, we have to differentiate by z the z transform of n power p minus 1. So this is the required z transform. So now we need to prove this. So LHS should be equal to RHS. So now let's consider the RHS, that is n of p minus 1. So now we know the definition of z transform of un, right? We have applied z transform of n tends to 0 to infinity un z to the power minus n. So this same thing we are going to apply it here also. So in place of un, that is n power p minus 1. So what would be the required transform? N to the power p minus 1. So here we can also, now we can apply the we have studied one property called as linear property. Here this term is there, right? N power p minus 1 is constant, so we can take that outside along with the summation. So what does this become right now? Into the differentiation of what is remaining here now, z to the power minus n. So now we need to differentiate this z to the power minus n. Just keep it as it is. So what is the differentiation of z to the power minus n? Minus n, this minus n we need to write first into z to the power minus n minus 1, right? So in the next step we can multiply these two terms, that is minus z into minus n. So it becomes, let's write the summation first, minus z into minus n is equal to zn into n to the power p minus 1 z into minus n to the power n minus 1. These two terms were remaining, so I have written it. So now we can simplify these terms further. So now we can simplify these terms further, as we can see that there are two bases which are same, that is n, and also there are two bases which are same, that is z, which also have, these also have some powers, right, that is z power 1 and n power 1. So we can write these bases together, that is, first we'll write it for n to the power p minus 1, and also there is a 1 here. So we know that we need to add the powers when there are same bases. Same goes for z. These two have the same bases, that is z, and now we need to add the required powers, plus 1. So here we can cancel this minus 1 and plus 1. So the remaining terms are n power p into z to the power minus n, which is equal to this. We can say that this is z transform of n power p, because in place of un there is n power p, so we can directly write it as z transform of n power p. By the definition we know that z transform of un is equal to un into z transform of minus n. So in place of un there is n power p, so we can write directly as n power p, and this matches with the LHS whatever we have proved. See, so we've took the RHS and we've proved the LHS, z transform of n power p. LHS is equal to RHS. So now we'll study some more further cases by substituting the values for p as 1, 2 and so on. So first we'll take p is equal to 1. So what happens now? In place of p, now it is substitute as n power 1. So now we'll use the definition of z transform of n power p, that is minus z into d by dz of z transform of n power p minus 1, right? In place of p now there is 1 minus 1. So z transform of n power 1 is n, right? So now here we need to find the standard z transform of n. So now what it becomes? Z transform of n power 0, right? This 1 and 1 will get cancelled and become 0, and we know that anything to the power 0 is 1. So directly we'll write it z transform of 1. So now we've discussed the z transform of 1, right? We have proved a general formula for z transform of 1, that is, we've proved it as z transform of 1 is equal to z by z minus 1, right? So now here we need to differentiate the term z by z minus 1 by using the u by v rule of the differentiation. We know that what the u by v rule says. The u by v rule says that we need to differentiate the v u dash means differentiation of u minus u into differentiation of v divided by differentiation of v square. This is the general u by v rule that we are going to apply for this case. That is, first the denominator term we need to write it into the differentiation of numerator, that is differentiation of z is 1 minus numerator as it is z into the differentiation of denominator, that is again 1. Differentiation of z is 1 and 1 is 0, divided by the square of the denominator. So now we will simplify this term. This becomes z minus 1 into 1 is z minus 1 minus z divided by z minus 1 whole square. This z gets cancelled, minus z into minus 1, so it is equal to z. Therefore z transform of n corresponds to z divided by z minus 1 whole square. This is the case when p is equal to 1. So now we have another case, that is we need to take the value of p is equal to 2. P is equal to 2. So now we will take it. So now we need to consider when p is equal to 2. That is, if we substitute p as 2, we need to find the z transform of n square. So here the main goal is for us here to find the z transform of n square. So now what this will become? Z transform of 2 minus 1. 2 minus 1 is n to the power 1, that is equal to n. So now we have also proved, previously we have proved the z transform of n, right? What we have proved? We have proved it as z divided by z minus 1 whole square. So again we need to differentiate this by using u by v rule, this function. So again we are going to apply the u by v rule. First term, that is the v denominator, into the differentiation of numerator, that is differentiation of z is 1 minus the differentiation of denominator, differentiation of this is 2 into z minus 1 whole square, right, into the numerator, that is z, divided by square of the denominator, that is z minus 1 whole to the power 4, because there is already a square, right? Square to the power square, again it becomes 4. So now we need to simplify these terms. So what is z minus 1 whole square? We need to use the formula a minus b whole square. If we substitute using the formulas, we get a square plus b square, that is 1 square is 1 minus 2 into 1 into z, 2ab, minus 2z square minus 2. Here 2 into z is 2z, and here we have again z, so we need to multiply that as well. Minus 2 into 1 is 2. 2z square plus 2z, because minus 2 into minus 1 is plus 2, and there is a z we need to multiply, divided by z minus 1 to the power 4. Here we can cancel this 2z, right? So the term that we have left is z square minus 2z square, that is equal to minus z square plus 1 whole to the power 4. If we multiply minus z to the term, we get it as z cube minus z divided by z minus 1 whole to the power 4. So now here in the denominator we can take one z minus 1 term outside. If we take the z minus 1 term outside from this term, the remaining terms are this one z term will come here, that is one z term would be removed, that we have taken it common, right? So this becomes z square, and this minus z would be replaced by plus z, because we have taken minus 1 z minus 1 outside, right, divided by z minus 1 whole to the power 4. So we can cancel this z minus 1 and 1 z minus 1 term. So this now the denominator will become z minus 1 whole cube. So the required Z transform of n square is z square plus z divided by z minus 1 whole cube. So please you all do make a note of this, because these z transforms you are going to use in many problems. These are just a few general forms. There are many more general forms we are going to discuss in the upcoming sessions. So this was all for this session. So in the next session we are going to discuss some more properties of Z transforms, and along with that we are going to start with the problems. So yeah, this was all for this session. Thank you.